with friction, the final mechanical energy is always less than the initial kinetic energy, initial total energy, okay? When there's friction in the system, your energy becomes less at later times. Less and less as time goes on. And that, of course, means that without friction, what will happen? E final is equal to E initial. This is called conservation of mechanical energy. All right? So if there is no friction, mechanical energy, meaning the total of potential and kinetic energy, potential energy due to all conservative forces, plus the kinetic energy of your particle, that number remains constant as the particle goes from here to here, does any kind of complicated motion. You are not interested in the complications. At each and every point, at every later moment in time during this motion, the total energy will be the same. So you can use that to find the final situation. Clear? Okay? When there is friction, this is not true anymore. The energy, the mechanical energy is not conserved. Kinetic plus potential, whatever it was initially, at later times it becomes less and less. Now, what happens when there is friction? Is the energy not conserved? Where does that energy go? Isı, okay, heat. Heat is the English term for ısı. What does heat mean? Where does the energy really go? Does it just disappear?
Energy never lost.
Yes, but this is the question I'm asking. Is it really never lost? So, when there is friction, okay, you can actually feel it, that it increases the temperature. There is heat. Heat is formed. What is heat? What is heat?
Another type of energy.
What type of energy? What's happening? Okay, now let's think a little more in detail. Let's think of friction. Remember what we said. What's the reason for friction is? When you have two objects in contact, the molecules in their surface are tangled. They interact with each other. They pull and push each other across the surface. Okay? This means these molecules are hitting each other, applying forces on each other, doing work on each other. And if you were able to look at the situation microscopically at the level of every molecule, what's happening to them, you will see that a lot of new kinetic energy is coming to these molecules because of the excitation by friction. Okay? That's heat. We sense that as heat. And it was proved by scientific experiments in the 19th century that if you include the heat carefully, if you measure the amount of energy in the heat and include it in your balance, so you say the initial energy, mechanical energy of the system, plus whatever heat was formed, okay, just measure it. Does that equal to the final energy? Yes. So when you take account of the energy that went, that leaked out to microscopic motions because of frictional interactions, if you take that into account, if you really go microscopic and were able to account for the kinetic energy and potential energy changes of all the little molecules and all the springs connecting them, okay, then you will see that the total mechanical energy, including microscopics, is conserved. But we are not able to keep track of the microscopic energy of every little molecule. Instead, macroscopically, we can still sense it, okay, because the temperature changes. We'll learn about temperature later on. But there's a way to measure macroscopically how much energy leaked into heat. If you take that into account, then you arrive at full energy conservation. Okay? Clear? Any questions so far? Now, let us start to use potential energy. The concept of potential energy, that is. How do you use potential energy? Well, first, in the given problem, you have to figure out what the potential energy is. Okay, and once the potential energy is given, you make a plot of the potential energy. To make it simple, at first I'll just plot potential energy as a function of x. I'll consider one-dimensional motion. Okay? And suppose my one-dimensional motion is just the motion of a block, a mass, that is attached to a spring. Okay? Bir noktayı tekrar söyleyeyim arkadaşlar. Bu derse devam zorunlu değil. Buraya geliyorsanız bu dersi öğrenmek için geliyorsunuz varsayılıyor. Bu derste başka kitaplar okumak, bilgisayarla, cep telefonuyla ilgilenmek hiç gerekli değil. Onu başka yerde de yapabilirsiniz. Buraya gelmeyin o zaman. The only condition for you to come to the lecture is to pay respect to other students around you. Not to interfere with my attention and other people following the lecture. Okay? Now I return to potential energy. Okay, so the example I'm considering is a mass attached to a spring. Okay, and you pull the spring and let it go. So the only force, I'm assuming there is no friction. Simplest situation. The only force is the pull of the spring. And we already studied in the previous lectures that this force is conservative. There's a potential energy, and we actually figured out the form of that potential energy. And now I'm going to plot it. So here's the potential energy U of x for my example. Okay? Now, suppose originally my object was at this position. For example, I pull this spring by 30 centimeters. Okay, so the initial x is 30. Okay? And suppose I also give it a velocity. I pull it and I give it a velocity and let it go. Okay, so the initial velocity was, let's say, 3 meters per second. Okay, let's say 2 meters per second. Okay, 3 meters per second, doesn't matter. And initial x was 0.3. And the potential energy, let's say, I'm just making up an example, is equal to some constant times x squared. I write that constant as k over 2. You will see why. We already did that, okay, to get a force minus kx. So suppose that is equal to, okay, 10x squared. So what's the initial energy? The initial energy is the initial potential energy plus the initial kinetic energy. So I have to choose a mass. Let's say my mass is 1 kilogram. Okay? Now the initial potential energy is 10x squared. So that's 10 times 0.3 squared plus the kinetic energy, which is 1/2. I have a mass of 1 kilogram. And the initial velocity is 3 meters per second. Okay. So I have here 0.9 plus 4.5, if I'm not making any mistake. Okay, so 5.4, and the unit, as we learned before, is called a joule. It's kilogram meter square per second square. Clear? Now, let me use my potential energy information. I have